another statistical class. Before I get started today, of course, we are currently grading exam 2, and also to let you know, final exam practice questions have already been published. I need you to check for that on Canvas. Okay, so today we're going to continue with chapter 14 that we started on Monday. And this is on analysis of variance, where we try to compare means in more than two groups. Okay, so the focus today is just to walk you through the procedure of conducting analysis of variance tests. And of course, I'm going to walk you through, you're going to see the ANOVA F test statistic, because when we conduct an analysis of variance tests, we use ANOVA F test statistic. So I'm going to walk you through all of that today. So, like I said, I'm going to walk you through the procedure for conducting ANOVA test. On Monday, I walk you through something like this. You know, if we're comparing means in more than two groups, there are two types of variations that are involved. The first one is variation between, and the second is the variation within. And let me tell you this, the test statistic formula that we're going to use is actually the ratio of the variation between to the variation within. But what I want to first walk you through right now, okay, so how do we get variation between? Okay, from data. And how do we compute variation within? Also from data. Because the moment you get variation between and variation within, then you you are all set to obtain the test statistic for ANOVA. Okay, so I'm actually going to start right now. I need you to pay attention. I think I explained that the other time. I'm also going to explain again. Now, I need you to pay attention to that. We want to figure out variability between groups. We are interested in how means of several group differs from one another. Okay, if I want to get variability between, that we call SSG, sum of squared deviation for groups. What I'm going to do, I'm actually going to be subtracting the overall mean, the mean of the entire observation put together, from each and every, from the mean of a particular group. If you take a look at the formula that I have here, I told you the other time, okay, if I have group 1, group 2, group 3, I'm just assuming, maybe we have 3 groups. We're going to take a sample size, N1, for group 1, sample size N2 for group 2, and sample size N3 for group 3. Now, from the sample size N1 for group 1, you're actually going to have a mean for that particular group. You're going to have a mean for this particular group. Okay, you're also going to have a mean for this particular group. Situation where you got three groups, you're actually going to have 3 separate means. Where you have 4 groups, you're going to have 4 separate means. Does that make sense? Now, you're also going to have standard deviation for each group. Standard deviation for that, standard deviation for that, and the standard deviation for the third one. And the moment you have standard deviation, you can also get the variance. All we just need to do is to square each standard deviation. That will give you the sample variance for each group. Okay, so that will be sample variance for each group. Now, if you put all the observation together, okay, then we're going to have this guy. That is the overall mean. Okay, when you put all the observations together, the overall mean is the y bar. Now, do you know what I'm trying to do here? What I'm trying to do here, I'm subtracting each mean. Let me tell you this. The SSG that I'm actually trying to do for three groups right now means, okay, for group one, what is the sample size? Okay, for group one, multiply by, I'm actually going to subtract um, the overall mean from the mean of group one. Okay, then I'm going to square that. I'm going to square that. Then I'm going to add, I'm going to go for for group two, N2. Okay, then the sample mean, okay, for group two minus the overall mean. I'm going to square that again. Okay, I'm going to square that. Then I'm going to go to the last one. If I have three groups, it's going to be the sample for the third sample, then the y bar 3 minus y bar all squared. Now, if you do that, if you add that together, you're getting the variation between group, which we call the SSG. Now, the moment you get a variation between group, okay, the next you're actually going to do is to get the MSG. The MSG is actually the mean square variation for group, which is going to be SSG divided by G minus 1. G is the numbers of groups. Okay? Now, that is the variation between. I'm also going to do variation within. The variation within is called sum of square error. We call it sum of square deviation for error. What am I going to do? Okay, for group 1, what is the sample size minus 1? For group 1, multiply by the sample variance of that particular group. Okay, you see that? Plus, I'm going to do the same to group 2. N2, okay, you know, you want to get this, you are computing this from data, right? Multiply by the sample variance for the second group. Then plus N3 minus 1. The sample for the third group minus 1 multiply by the sample variance for the third group. You see that? If you add them up, that will give you the sum of square error. Now, after getting that, then you're going to get the MSC, which is going to be whatever you get divided by N minus G. What is an uppercase N? The uppercase N is the totality of all the sample size. The uppercase N is equal to N1 plus N2 plus N3. Okay? So that is that. And let me tell you, the moment you get the error between and error within, the next is to get the overall variability. Overall variability is adding SSG to SXE. Okay? Now, let me show you the ANOVA F test statistic. This is the ANOVA F test statistic. You can see I said something the other time. The ANOVA F test statistic is the ratio of variability between divided by variability within groups. And let me tell you this. I need you to pay attention so that you can grab it. When F is large, you know what is going to make F to be large? When the numerator is large. You know, when variability between group is very large, F is going to be large. When F is large, the p-value will be small. When p-value is small, then you are likely going to reject H naught. I'm going to say that again. When the variability between is large, F will be large. When F is large, the p-value will be small. When p-value is small, then there is high chance you're going to reject H naught. When the variability within group is large, now when the bottom is large, F is going to be small. When F is small, the p-value will be large. When p-value is large, you will fail to reject H naught. Okay? Now, you know what I want to do now? I quickly want to walk you through the procedure, and I need every one of you to pay attention if I want to conduct analysis of variance tests. If I want to compare means in more than two groups, what are the procedure? You remember when I was walking with you through chapter 10, when we were conducting hypothesis testing of means and proportions for two populations, we go through step number 1 to step number 5. Now, let us look at the step here. Number 1 is assumptions. Okay, assumptions for analysis of variance. There are so many. We got 3 of them, and I need you to pay attention. Number 1, you must be taking random sample from the group, from each of the population. You remember we did the same when we're comparing two groups. We took random sample from each of the group. Okay? So G independent random sample from G populations. G represent the number of populations or the numbers of groups. Number 2, the population, each population we're choosing from must follow normal distribution. Each population we're choosing from must follow normal distribution. Then number 3 in the assumption is each population, all the population, they must have equal variances or equal standard deviation. We're not talking about sample variances. We're talking about population variances. Population variances and population standard deviation have to be the same. Now, these are the assumptions in analysis of variance. You remember the next, what is going to be the next? Test, is the hypothesis formulation. I need you to pay attention. Okay? When I'm comparing the number, if the numbers of group is G, I'm going to have that. But let's say, for instance, you only have 3 groups. I'm gonna write something now. When you have 3 groups, the non-hypothesis here is just going to be mu1 equal mu2 equal mu3. You're actually going to stop where, depending on the number of groups we are comparing, this is going to be H naught for situation where you got 3 groups. Alternative remain the same all the time. Alternative is always going to be that at least 2 of the population means are equal. Does that make sense? Now, the next step is the test statistic. Now, this is where we're going to spend a lot of time. Okay? I need you to pay attention now. I need you to pay 100% attention. The F statistic is the ratio of MSG to MSE. For us to be able to get this, we need ANOVA table. I'm going to say that again. For us to be able to determine our test statistic, because let me tell you this. Whenever we are actually testing means in more than two population, the distribution is F. You remember the other time when we're testing hypothesis or mean, when the population standard deviation is known, we use Z, that will follow Z distribution. When the population standard deviation is unknown, you normally see that will follow T, right? But right now, okay, for analysis of variance, it follow F distribution. And that's why you see us having F. Okay? Now, you know what we're going to do now. This particular area, test statistic, getting F, will take us to ANOVA table. Now, I'm going to show you the ANOVA table now. Please pay attention. Okay? You know, when you are in the F statistic, the text, the statistic for F, for ANOVA, you will draw ANOVA table. Now, in the ANOVA table, you need to write, you need 4 columns or 5 columns. 1, 2, 3, 4, 5. The 4 of us write the columns. Source of variation, degree of freedom, sum of square, mean square, and F. Now, after writing that, you write group, you write error, you write total. Because analysis of variance will enable us to measure variability between groups and within. Okay, within is the error. Within is the error. Within group is the error. Between group is group. Okay, then we have total. Now, after you have written all of that, the next that you're actually going to write is here. You need to fill up this place. Okay, all the time is G minus 1. If you are having 3 groups, if you are comparing 3 groups, that will be 3 minus 1. And what you're going to have there is going to be 2. If you have 4 groups, that will be 3. If you have 5 groups, that will be 4. Does that make sense? Now, after that, you go to this guy, n minus G. What is n? N is the totality of the sample size across groups. G is the numbers of groups. You do that. And after that, you're actually going to get that, which is the totality of the observation minus 1. Let me also tell you this. Do you know that this, if I know this, and I know this, if I add them together, it's actually going to be equal to this guy. Please take notes. Now, in the ANOVA table, I got 3 degrees of freedom. In the ANOVA table, the first one, G minus 1, that is the degree of freedom for the group. N minus G, the degree of freedom for error. N minus 1, the degree of freedom for total. Is there any question? The very first column, okay, that you're going to complete is the degree of freedom column. Now, after getting the degree of freedom column, the next column is SSG, SSE, and SST. That was the one that I explained before. Give me 1 second. I'm going to show you. That was the one I explained earlier. Okay, is this guy here. Okay, using this formula, you're going to get your SSG. Using this formula, I showed you before, you're going to get your SSE. And when you add SSG to SSE, that is going to give you the SS total. Okay, so using those formula, you're actually going to get that. Now, the moment you get that, you already have all of this decided. You have this one now, you have that one now. And let me also tell you this plus this is the same thing as this. And this plus this is the same as this. Look at that. G, when you add G minus 1 to M minus G is that. When you add SSG to SSE is this guy. Now, do you know that the moment the first 2 column is well computed, The other column will be easy. Now, let me tell you, I'm in this column now. If I want to get this guy, it is this divided by this. Look at that. If I want to get that guy, it is that divided by that. The moment any of that is wrong, this is going to be wrong. If I want to get this guy here, it is this divided by this. You see that? That divided by that give us that. That divided by that give us that. Now, where are we now? We are here. We are here now. We are here now. If I want to get my F is this divided by that. Can you see that? Can you see that? You can see, finally, we're going to get that. But getting this, you have to start from there. Okay? We need an ANOVA table to get the ANOVA test statistic. Okay, now after that, okay, after that, we will be able to obtain our F, the test statistic. And let me tell you this. You remember when we were conducting hypothesis about mean, where population standard deviation is unknown, we use t-test. And of course, if you want to get p-value, it was pt, right? P-value, it was pt. And inside the pt, we indicate degree of freedom. Now, let me also tell you this. When you are working with F has two separate degree of freedom. This guy and this guy. Now, I'm going to show you the degree of freedom from the ANOVA table. The degree of freedom that we need in F, the first degree of freedom, that guy, the second degree of freedom, that guy. We only need those two. Okay? Now, for me to actually tell you, so after that guy now, you got a p-value, right? And the p-value is going to be this. And some of you may be wondering, why greater or equal to? I'm going to tell you now. Okay? The reason why the p-value is going to be the probability of F greater or equal to that is because F distribution is a positive skew distribution. Okay? Before I take you to there, of course, conclusion remain the same. Conclusion remain the same. Now, let's quickly look at properties of F. This is the shape of F distribution. What do you see? Always skew to the right. You remember under T, right? T could be, it could be skewed to the left, skewed to the right, or even balanced. But here, you can see this skew to the right, non-negative. You know the meaning of non-negative here? Non-negative here means the value that you're going to get after your F all the time has to be positive. There's no negative. Why? Because each of that, don't forget, you square something. You remember? When you square something, you're not going to have negative. So whenever you compute your F and you have a negative, that's a red flag. Does that make sense? F is always positive all the time. And even in the table, if you check in the table, there is no any situation where any of the entry is going to be negative. It's not going to be possible. The moment you get negative at any junction in the table, then that's a red flag. It means you need to go back and maybe you made a mistake. Does that make sense? Now, it is a right skewed, okay? The mean is approximately 1, the mode is that. But you know what? What is the code for p-value? I need you to pay attention now. For p-value, you remember when we were conducting t-test, what was the code for p-value? pt, right? After writing a pt, inside parentheses, you write a test statistic value, right? The degree of freedom. Let's take a look at this. For F, take a look at this. PF For ANOVA test, the p-value is PF, not PT, not P norm. What will be the first value? The first value you're seeing will be the value that you got from the F ratio. The one you get from the table is this guy here. You see that guy? Then we're actually going to have two different degrees of freedom. The first degree of freedom is the one that I call G minus 1. G minus 1. The second degree of freedom is the one that I call N minus G. Then all the time, when you are finding a p-value for F, it's always going to be lower F. Why lower F? It is lower F because it is always it's always greater or equal to. So it's going to be lower equal to F all the time. So when you are writing the p-value all the time, it has to be lower equal to F. Now look at the second one. The second one is when you have a different F ratio and you have two different degree of freedom. Now let me quickly walk you through. You remember on Monday, I talked about comparing means from three groups. The first group was behavioral therapy. The second group was family therapy. And the third group was no therapy at all. Okay, based on the data set, I think we were told on Monday they used 72 teenage girls, right? 72. Now I'm going to show you the ANOVA table. Now, why do we have two here? Because the numbers of group is 3. 3 minus 1, 2. Does that make sense? That's why you have that. Now, why do we have 69? Okay, you know, the formula here, we use G minus 1, right? The formula here, we use N minus G. Okay, what was N? N was 72. They told us on Monday. So what is 72 minus 3? 72 minus 3 is 69. Does that make sense? And do you know, the moment I have 2 and 69, I can get the degree of freedom for total by adding that. I can say 2 plus 69, that's 71. And another way, if I don't want to do that, I can also use this. You remember? Capital N minus 1. Do you see that? Some of you may be wondering, where do I see all of that? It's right here in the ANOVA table. Do you see them? Oh, sorry. It's right here. Do you see them? The first column. That is the first thing you're going to do. Now, they've already, they've done the second one. Now, after that, they go to the SS column. Okay. They've computed these two. Okay. Using the formula, they've computed those two. And the moment you get these two, this is going to be easy. This plus this is this. Imagine an exam where they declare some missing and they wanted to figure it out. I needed to understand the relationship now. So this plus this is this. And do you know that the moment I got these two, if I divide this guy by this, I'm going to get this. If I divide this guy by that, I'm actually going to get that. Look at that. 614.6 divided by 2. 3910.7 divided by that is this. Okay? You see that? Which means, do you know at times if they give you this, and this is missing, I can just do this multiplied by that will give me this. This multiplied by that will give me that. So this divided by that is this. Now, the moment I know this, the moment I know MS column, the moment I know this, and I know this, it's always going to be this divided by that to arrive at this. You have to be very, very careful. This is the F statistic. Whenever we want to get ANOVA F statistic value, we have to start, we need an ANOVA table. Now, after, so let's say you, after getting that, let me show you the hypothesis in the first place. Do you see the way, do you see, look at the assumptions? Okay. How am I going to know? You know, the first assumption said that they have to be random samples, right? Okay, you have to look at the question whether they mention random sample. And another assumption said that the distribution has to be normal. Okay, you can do a box plot to see whether each of the, that was what I said, from box plot, we do a box plot, we actually going to see. Then the equal variance too, okay, we'll be able to see whether they have equal variance. And of course, after that, hypothesis formulation, because I only have three groups. You see that for three groups? For three groups, me one equal to me two equal to, the alternative, at least two of the means are equal. Then the test statistic value. You actually, in the test statistic value, this one, you're going to go back to the ANOVA table. Okay. The test statistic value is this value that you got here. The value that you got here. If it is wrong from day one, is this value is going to be wrong. And don't forget, you need this value for p-value. Okay. Now that value now is what I state here. After that, the next is to go for p-value, right? Look at the p-value now. Please pay attention. What did I do? PF 5.42 that I got in the ANOVA table, comma. Now, with a 2 degree of freedom, I'm going to take you to the degree of freedom. You know, here they say 2 and 69, right? Let me walk you back. Do you see? It shouldn't be 69, 2. It has to be 269. It has to be whatever you see, it has to be the way it appears in the table. Does that make sense? 2, comma 69. Okay. So right now, 2, comma 69, and don't always forget lower equal to F all the time whenever you are conducting an ANOVA test. And that will automatically give you this guy as a p-value. Okay. So the p-value here is 0.0065 automatically. So like I said, whenever you want to get a p-value for ANOVA, it's always going to be PF. PF. Remember for t-test, it was PT. For hypothesis testing under proportion, we use a p-norm. Now, for ANOVA, we're using PF. Now, if you look at this p-value now, it's 0.0065. Okay, it's actually greater than, it's less than the level of significance given. So the level of significance is 0.01 or 0.05. That value is less than that. And when it is less, then you're going to come to conclusion. Okay, conclusion is rejecting H naught. And this is where you're going to say reject H naught and conclude that the mean weight gain is different for at least two of the groups. Okay, it's different for at least two of the groups. Go ahead. 2, comma, you mean right here? Oh, okay. You know, this one, we're not using that. That is NIST. There are different ways. But in this class, we're using R. Okay, there's so many software, MATLAB, Python, uh, the SAS. There are so many. But I'm just trying to say there that, okay, maybe for those who are using NISF table, we're not using NISF table. We're only using a R, and that's why the code PF. Does that make sense? Okay. Now, this is where I need you to pay attention now. The conclusion here is that the mean weight gain is different for at least two of the groups. The question is, which ones? Analysis, when you reject H naught in analysis of variance, it will not tell you where the difference lies. I'm going to say that again. When you are comparing means in more than two groups, when you are comparing in two groups and you reject, you know where the difference lies, because you know that, oh, the mean here is greater than the mean here. But this is three. So the question is, which one? And that is what we're going to do on Friday. That is what that's what I'm calling this. Follow up to the ANOVA test. Follow up to the ANOVA test is going, okay, after we have rejected the null hypothesis, where does the difference lies? Which of the group has a significant weight gain? And that very question cannot be answered by ANOVA test. The ANOVA test is only going to tell us different exists, different do not exist. That's all, period. Now, let me quickly show you in R. Please, I need you to pay attention. Let's say, for instance, we give you assignment. We give you assignment. Please pay attention now. Whenever we give you assignment, we give you data, right? Now, let's say this is your data. This is your data. The code here, the code here is to get your data set. Okay? If you try to type that into R, okay, that will enable you to import your data set. Now, the data set on this same research, in this research, we are comparing the weight gain in three groups of therapy. The first one, family therapy. Oh, sorry. The first one was behavioral therapy. Second, family therapy. The third, no therapy. Now, if you want to have access to that data, that anorexia data set I said, copy that into R. Now, I need you to pay attention now. If you copy that into R, what is the code? Do you know what is going to happen? If I write a simple code, R will automatically generate ANOVA table and the p-value. I'm going to say that again. Do you know if I write a simple code, R, we save you from unnecessary stress of doing computation using the ANOVA table. R itself, we automatically generate the ANOVA table and the p-value. Now, what is the code? Please pay attention. Please pay attention when you have your data set in. This is the code. Okay, AOV. You know what AOV means? Analysis of variance. You must write that. Now, in the data, response variable is change. Like you want to see whether there's a change in weight. Does that make sense? The response variable is change. Then therapy here is categorical variable. Okay, it's one of the variable and it has levels. How many levels? 3 levels. That's why we have 3 groups. Okay, behavioral therapy, family therapy, no therapy. That's that. Do you know with that simple code and you do summary AOV1? Oh my God, it's going to automatically generate this for you. Do you know what's generated for you? The only thing it's not going to generate for you is the total. The total is missing, right? We don't need total. Now, you see 2 and 69, you saw it the other time. Automatically, it has computed everything up to the F value and even up to the P value. The reason why we make use of software, the software will enable us to save enough time of computation. Software, the role computer play in statistics and mathematical world, research world cannot be overemphasized. Imagine if we have data set that we want to compute the table, ANOVA table, it's going to take forever. But with a simple code, we have our table generated. Not only that, we even have our p-value generated. Now, right now, looking at the p-value, this is the same p-value, 0.006499 that we got the other time. Take a look at that. Is it not this one? When we try to do it, one at a time, it's the same p-value. So how do we automatically generate that? And of course, looking at the p-value, if you compare with the level of significance given, it's going to be less than. And what is going to happen is that there's a significant difference in the means. But the issue that we have right now, we don't know where the difference lies. ANOVA, analysis of variance, will not tell you where the difference lies. Okay, now after rejecting the non-hypothesis in analysis of variance, if I want to know where the difference lies, then I need to do what we want to do on Friday. What we want to do on Friday was given by Turkey, okay, where we have a comparison test. We're actually going to have a POS comparison test after we have rejected H naught. Let me tell you this. If we fail to reject H naught in analysis of variance, what we want to do on Friday is not necessary. I'm going to say that again because where different don't exist. If I compare three groups and they say different don't exist, then I don't need to look for where different lies. I'm only going to conduct what I call a further analysis if different exists. When we reject H naught, a follow-up to ANOVA is needed. And that is what I'm actually we're gonna go through on Friday. Now, let me say it before I go. Because final exam has a huge weight. Okay? Final exam has a huge weight. And that was the reason why I decided to publish the final exam practice question and solution very early. If you go to the canvas right now, okay, you're actually going to see final exam questions, the areas it covers. I'm going to release a study guide very soon. I'm not going to quickly release study guide this time around because I'm also going to wait because we used to be ahead in this session. Don't forget, we got several sections of 3011. Now, I need you to pay attention, get yourself get yourself familiarized with the contents of final exam practice question. Check the way ANOVA question is given because I am 100% confident that your ANOVA will be part of final. Now, if you look at the way ANOVA, at times, maybe they've run the analysis for you. Okay, maybe they gave you the arrow output and maybe they just wanted to answer some question. And at times, they could give you some information and maybe probably some values are missing in the table. Some values are missing in the tables and they want you to use your mathematical knowledge based on the relationship. Imagine maybe this guy is missing and this guy is missing. If I want to get this guy, if I want to get this guy, I need to multiply this by this. Because for me to get this guy, we divide this by that. Don't forget, the division is the inverse of multiplication. You know, some of you, when you were in your high school, and that is why I want to say this. Use this opportunity to appreciate your teachers in high school because they are doing a lot. Because in high school they've exposed you to different kinds of algebraic operations where you multiply, you divide, you do this, you do that. Now you're going to be applying that now in college. Okay, so appreciate them. They really doing a great job because at that time you may not even know. Just like the way my daughter used to ask me, why are we dividing? Why are we multiplying? Well, now without mathematical knowledge, okay, before how, let me tell you something. The software that we're using, okay, that give you a result on time, the program formula behind the scene. If there's no formula, the computer is not going to do anything for you. So everything starts from formula. And in the formula, the knowledge of algebra is needed. When we talk about algebra, we're talking about multiplying, dividing, adding, subtracting. That is what we call algebraic operation. Okay? So the teachers in high school, in fact, not only high school, starting from the elementary, they're doing a very great job. This is why I'm going to stop today. So on Friday, uh, I'm actually we're going to do a follow-up to analysis of variance. Make sure you stay safe and have a lovely day. Bye for now, everyone. Exam earlier because I'm studying. When did you send it? Sent it yesterday. Oh, okay. I'll check. Okay, okay. But Oh, so I'm gonna attend to that. Let me take an into